do it. Do it.
Hello, Internet. So today we've got our very own JonJon, who's going to be teaching us some really cool stuff about how to recognize handwriting and how to recognize characters that are drawn by hand using machine learning. So take it away, JonJon.
Sick. Thanks, Jason. How's it, Denim? How's it, Naz? Hope you guys are all doing well today. Hey, how's it, Marvin? What's up, brother? Today we're going to do a little bit of I'd say even a cool crash course, a bit of an overview of how to sort of approach this problem, how it's actually done, a lot of different ways to solve it. So to start off, as Jason said, sort of the idea is, can you create a program that can recognize handwritten digits, for example? And this might be useful, say a government wants to just scan all of these photos in and recognize ID numbers and then put it in a database, so they don't have to have someone manually do it, right? So what does our data look like? I guess that's the starting point before we get too much into it. So I'm going to show you over here. I have this big CSV file called train digits, and you'll see the first column is the digit. So this is a 9, this is a 5, this is a 7, and these are essentially sample digits. And
so
you can
hold up, Jason. Will you put the
I just realized you guys can't see my screen. Hold on.
Okay.
Yeah, that's a good view. There we go.
Sick. Can you guys see it now?
Yep, perfect.
Yeah, I love the color
Nice.
code in the background there.
Yeah, so it's quite a cool little add-on in VS Code to color code your CSV files. But you can see the first column is sort of the important one. It lets us know what number this is, a 9, a 5, a 7, or whatever, the example. And based on that example, it gives us all of these pixel values. And you can see all of these first ones are sort of actually 0. And if you think of a box, I think this is about a 64 by 64 box. So for every single pixel in the entire picture, it will give us an RGB value. So you can see as we start going to the right here, you'll start to see RGB values, and I think it will be on a scale from 0 to, I think I might be using the wrong term, but from 0 to 256 to basically give the intensity of the writing over here. And you can see that will go across for all of our pixels. And let me just check how many pixels we have so I can remember correctly.
Do you mind making it full screen and maybe zooming in slightly?
Yeah, so 784 pixels. So that's, I think, 24 by 24. It's not, 900 would be 30 by 30. So it's something like that, 24 by 24. So little images of handwritten digits. And we basically now want to create some machine learning model such that whenever we see handwritten digits, we can predict them, basically. So how we go about doing that, before we get into it, there's a couple quick things I want to talk about. And let me just quickly make my screen big. Let me know if you guys can see this. Continuous scroll. There's this really awesome book, An Introduction into Statistical Learning, which is, I think, like a great way to sort of understand machine learning and what it actually does. And there's one or two quick things I'm going to talk about in over here. We'll come back to this content page. But the first thing I want to talk about is what we're actually doing and what our goal is. So our goal is we have a number of inputs or predictors, what they call them. So this X over here, you might think of them as independent variables, features, predictors, and those are all the pixels. So remember, we have this value of all the pixels. These are our X. And given all of these pixels, our input features, we want to determine the output variable, the response or the dependent variable. So given all of our pixels, our predictors, we want to determine what number is actually being written, the response or the independent variable. And machine learning is essentially constructing a function f of x such that this function will take in all of these inputs, all of these different pixels, and allow us to predict what this response would be, this y. So whether it's an 8 or 7 or 9. So as you can see, and what's highlighted here, in essence, statistical learning refers to a set of approaches for estimating f, this function over here. So our task is really creating a function, and this function would then take in a number of different pixels and allow us to infer what the response might be. So they call it machine learning because in order for us to construct this function, f of x, what we are doing is we are going to use a whole lot of examples. So here you can see we have the response variable y, and we have x, all of the inputs. And again, we have another example of the response y, and again, all of this inputs. So based on all of these sort of observations, and this is our data to sort of train our function, we can then train and create a function that will then be able to estimate if we were just given not the digit. So imagine we weren't given the digit, but we were given all the pixels. Now we have a trained function that will allow us to help identify what digit it may be, give it a prediction. And there's two reasons why we would actually want to sort of estimate this function, f of x. And the main reasons are prediction, as you already said. So given a whole bunch of pixels that we've scanned in our machine, we want to predict whether it's a 7 or 8 or a 9 to sort of populate our computer sheet. But the other one that's a little bit less obvious is inference. Maybe we are interested in knowing which pixels actually very much influence the output of the number. And to make this idea more concrete, it might make sense in saying, imagine all your predictors were to predict whether an insurance claim was fraudulent or not. And the predictors were the person's age, how many times have they claimed before, what's the value of the item they're claiming for, and then the output is whether the claim was fraudulent or not. In this case, inference might be very interesting, as you're very interested in knowing which predictors, such as, say, the person's age or claim history, have a very strong predictive ability of being able to determine whether that person has a fraudulent claim or not. So that's inference. It's understanding those predictors and how that influences your prediction y over there. So we won't get too much more into that, but I'm just going to first stop here and check, is everyone sort of following where we are at right now? Is everything clear?
Oh, great.
Awesome. Shot. So yeah, that's our start, right? So again, we're just going back to it, and now we are trying to create this function f over here. And I'm going to bring up this mark book, and I'm going to first say the first few things we are going to do over here. I'm just going to run a few chunks. We are just going to basically get this data in a nice shape, and in order for us to sort of test how well our model has done, so we've just been given all of this data, right? We're going to want to split up this data. Let's just say there's 1,000 data points right here. We are going to want to train our model to try get this function f of x on some of the data, let's say 800 data points, and then we want to test how well our model does on some of the other data points. And the reason we don't want to use all 1,000 data points to train our model is because then we would be testing our model on the exact same data that it's already used to learn. And in that way, it's sort of unfair, and your model will have biases built into it because it might not be able to extrapolate and predict examples outside of your sample size. You basically want to test, given an example it's never ever seen before, will it actually be able to predict it? So that's why we have something where we split it into sort of, they call it training and test samples, because you want to train your function and create it using some set of data, And then to see how well it's doing, you want to use another fresh set of data that's completely different and it's never been used to estimate your function. So I'm going to run this next chunk over here, which basically does all of this. This is a RMD file, so it's like a R markdown file, and you like can sort of write stuff in between and then put like chunks of code here and do stuff like that, which is quite interesting. And what I'm doing here is you'll see the plots. I'm sort of just checking the types of numbers there are. I'm checking the breakdown. So of our sample of everything here that we're going to use to train our function, I'm doing a plot, and just this will show you this plot over here. An example, if we map this 24 pixels by 24 pixels, this is what they look at, the examples. And in the corner, I've just plotted the labels. So this is a 4, this is a 7, this is an 8, this is a 0. And you can see like this is an 8 and this is an 8 and this is a 3. This one's quite hard to see. You can imagine it's not so straightforward or easy even for a human to decipher these. So it will be impressive if we can get a computer to do it perhaps more accurately. And this is it's always good when you start out your machine learning approach, just to get a better idea of the data you've been given. And this is the number of examples we've been given for each digit. So there's quite a lot of 4s and there's quite a lot of 9s. And I think people confuse 4 and 9 often. So I'm guessing they've included more 4s and more 9s so we can get an even better example of differentiating between the two. So as you can see, what I'm doing here, random select, all I'm essentially doing is creating a different training set and a different test set. And the X's and the Y's that I'm separating out are obviously just the predictors, so all the pixels, and the Y's are the result, the dependent variable, what the digit is. So I'll run that again for you guys over here. And basically now what I'm using, this K and N over here, this is already the first machine learning model we've done, and we've got 95% accuracy. So straight out the box, this is pretty insane. And if you see how little code this is, you got to think, what on earth is actually going on here? So the thing with R is a lot of these machine learning models have functions that allow you to straight out the box in one line of code train a model to actually predict something. So K nearest neighbors is one statistical approach to do it. We won't go into it too much. I'm just going to quickly scroll through and assess it. But essentially, yeah, this is a form of K nearest neighbors, with the nearest neighbors being equal to 10, and it's a type of algorithm that sort of yields a decision boundary, and I don't think we're going to go into the details of it. But most of these statistical methods will be trying to train the model and minimize and create some kind of a loss function. So you can see, can you guys see if I zoom in over here? The input parameters for this K nearest neighbors function is all of the training predictors for our training set, all of the predictors for our test set, all of the actual results for our training set. So it's going to use these to learn our training set. And then we're also giving it on our test set just the pixels. And then from that, we're getting what this model, K nearest neighbors, is actually going to predict. And this function mean is just saying on average, how well are our predictions from our K nearest neighbor model actually equaling what the result is from our test set. So this is a simple K nearest neighbors way of doing it. And already we've got like super high out of the box accuracy. And it shows you sort of how easy it is to get, if you know sort of the very basics, how easy it is to create machine learning models. But the big thing is all of these machine learning models have something called hyperparameters. you'll notice the last argument here is something called k is equal to 3. And if I go down to the bottom here and I go k nearest neighbors, what's really nice about R is I like this help thing that comes up, classification, and it can show you the different types of things over here. But essentially, k is the number of neighbors considered. And these are different hyperparameters in your function model. And if you haven't sort of studied the underlying statistics behind it, whether you put k is equal to 3 or k is equal to 50, we can now run this chunk again and see what our accuracy is. You can see if k is equal to 50, it will take a bit more time to calculate. Our accuracy is only 90%, whereas when k was equal to 3, our accuracy was 95%. So a lot of machine learning is actually learning the statistics behind how this k nearest neighbors algorithm works. And based on the data you're given, it's understanding what these hyperparameters should be and having a good feel for what would produce the best model that would give you the best results. So a lot of it is very easy to just do out of the box, but the hard part is understanding the statistical properties of the method so you can use the correct hyperparameters to get the best result. And what you don't want to do is something called overfitting. And overfitting would just be, let me run a for loop, an algorithm, where I just loop through values of k from 1 to 100 and just pick the k with the best result of accuracy. Because what you're doing is you're overfitting to a specific data. So we are just training our algorithm on this certain amount of data. And if you brute force, just try find the best hyperparameter for that specific set of data, it's unlikely that that might be the same k for another different set of data. It's like a way of fitting too closely to your test data. You're putting too much weight on your test data, on your training data, and you're training too closely to these 1,000 examples, so it might not be able to have the same predictive power on other data. So I'm going to first stop there now and maybe field some questions. I don't know if you guys have any questions before I go a bit further and keep hearing my own voice. Is there any thoughts so far?
Hey, John, I do have a question.
Awesome.
It is about the data set size. What is the optimal data set size? I've read somewhere that it depends on the degrees of freedom in the model.
Yes, yeah. So that will, so I think optimal size, I'm not 100% sure there's like a golden rule, but generally the more data you have, specifically in supervised learning, it often helps to have more and more examples, because you can imagine if you only have 100 examples and a few examples of these digits each, then it becomes very difficult for you to actually create a model. Whereas if you just had 1 million examples, you would have lots of data to train your model on, plus you would have lots of data to then test your model on and validate its accuracy. So in this case, I would say in this supervised problem, the more examples we have, pretty much the better. But there is the case where some statistical models, like k nearest neighbors, etc., depending on how many predictors they have. So right now we have 784 pixels. So we have 784 predictors. So I'm just going to write here. So x is equal to 784 predictors, and the number of observations we have, okay, so we have about 10 by 250. We have about 2,500 observations. In a lot of cases, algorithms, there'll be some type of rule. So if you have 784 predictors, you should have at least 10 observations for every predictor you have. So you should have maybe 7,840 observations in order to use that algorithm and for it to be stable. So depending on the thing you're using, that's where it comes into account. And when you're talking about degrees of freedom, that is essentially talking about how many predictors you have. And in this case, we have loads of predictors. So yeah, your observation size, dependent on the algorithm, should take into account how many predictors you have. And some algorithms perform very poorly if there's a low ratio of observations to predictors, and some are more robust and they can handle it just having less observations. But yeah, that's if my memory serves correct, but I'm sure there's people who have better answers to that one. Cool. Any other thoughts or questions so far?
Yeah, one more. This is not exactly related to this model, if that is okay.
Yeah,
if not, I can.
Sure. No,
yeah?
no. Ask ahead.
What is an XGBoost model? I've always wondered. I think it's just an ensemble method.
Yeah. So from what I understand and remember is a lot of these are tree-based methods, and we'll get to it in the book now. But the first one we talked about was k-nearest neighbors. So now's a good time to talk about it, because I actually do use boosting as a method of doing it. So excuse my looking, but you guys will be familiar with linear regression. Actually, linear regression can be a very basic model to get a linear model based on your observations. So I'm going to answer your question now and get to it. Trees should be somewhere here in the book. You can see I've read this book a few times and highlighted the sticks out of it.
I like your colors. Each one probably means something else, right?
I actually wish it does, but to be perfectly honest, I just use different colors because I get less bored using different colors. Sorry, guys, we're going to get to trees now in a second. Classification. There's probably a better way to do this. Okay? Okay, maybe not. Two seconds. All right. Step functions. I'm just going to quickly go to the index and zoom. Yes, sorry, I should have done this a long time ago. Moving beyond linearity, tree-based methods. Okay, 303. So quickly over here, you can see you're talking about XGBoost. I think that's a package that implements boosting. Decision trees are pretty interesting. It's a way of growing out your decisions. It's another way of creating that function f we're talking about. And there's basically three main tree-based methods: bagging, which is the initial one, and then random forests and boosting, which are both improvements over it. But bagging, let's quickly go to page 303. And we'll create some of these models now. I just want to show you what a tree looks like quickly. Actually, I'm going to show you in here because I do create a tree here anyway. So I'm just going to run these other ones quickly. Anyways, you'll see we get to the trees now in a second. I did some more advanced k-nearest neighbors, and I played around with a lot of different ways to actually do it. Here you can see in this accuracy, I also drew this diagram that shows all the digits, and it shows the actual versus the prediction, and you can see the digits that it sort of got wrong most of the time. Seems like it's predicted 9 quite a lot when it was actually 8, for example. You can also see it's predicted it's actually been 4 a lot, and the prediction has been 1, which is quite interesting. So this is a nice little visual way to see your predictions and how it looks. And I'm going to run this chunk over here. So Naz, I'm still getting to your question, bro. Don't worry, I haven't forgotten. So yeah, I'm just running through some of these other models quick, and we'll get to trees. So this is using cross-validation. And remember, I said it was very important for us to split up our data into training data and test data, so that we could use one to train the model and one to sort of see how well our model is done, essentially. There's something called cross-validation, and what it does is, I'm going to get to a better diagram of it. It splits your data up into, say, n parts. Let's just say 10 different parts, and 10% of the data will be used to test and the other 90% to train, and then it switches it, and then it uses the next 90% of data to train and then test on the remaining 10%, and then it keeps doing that for all these different folds. So it creates lots of different training and test sets, and this is hopefully to allow your model to actually train through all your data while not sort of having any like memory leak, and actually training and testing on the same data at any point in time. So this is the cross-validation, and you can see the average accuracy using k-nearest neighbors methodology via cross-validation is 0.958. And I think that's a slight improvement on 0.956. So in this case, it's just a small improvement compared to earlier. This was a pretty hectic one I used, using histograms of gradients. That got a really good result, but we won't go into that. It's also using cross-validation. Okay, so here I'm going to show you the tree. We're getting to the trees now. I'm just going to wait for this one to run. And let's get to this diagram of trees back down here.
May I just jump in for a second again? In cross-validation, you have, like in that case, you would have 10 folds, I think. And
yes.
So would you pick like the best one, or are they like somewhat combined?
So I'm gonna not remember the exact details. It's been about a year and a half since I've gone through this literature, but from what I understand, it uses, I think, an average across all of those. I don't think it uses. Otherwise, it's a bit like overfitting. If you sort of just choose the model that's got like the best results based on that data and training. So I think it doesn't choose the best one. I think it averages across all of those trainings, across all of those folds. Cool. So I'm pretty sure it does something like that. You can see this one's got accuracy using of 0.977, that method. Cool. Now I'm going to go through next one. So another thing you do is, before you even do machine learning model training, you can do optimizations to your data to give your models better results when learning. So if you look, for example, here, check how much wasted data it is. Like, all of these are all 0. And you can see that by the fact that, you're not getting much data over here. There's lots of just empty space. All of these pixels, this top left pixel is never got any data in it. So some of those predictors are very meaningless, and you can use other statistical methods to sort of determine which predictors are super useless and remove those from your analysis. So that's another cool optimization that you can do, and often in machine learning you can do things like that. So you can see over here, from 784 pixels as predictors, we've removed 145 that are completely useless and sort of give us no predictive power. Cool. So now I'm going to be loading the library tree, the package, and sort of plotting what a tree looks like. And a tree basically at every point will split between a predictor, a pixel, 784 something, and it will go left or go right. And it will say, depending if it's this, you should go left or you should go right, like a tree-based methods. They're very easy to explain to people, this textbook says. So you can see over here, you'll have a number of different predictors, and this decision tree will say, if its CA is less than 0.5, go to this part of the tree. If CA is greater than 0.5, I'm sure it's a typo, then go to this side. And then at the end of the day, you'll have a no or a yes based on the example filtering down every decision part in the tree. So that's sort of what a tree does. And to get to your question, bagging just creates a whole bunch of trees and averages them out. And it considers every predictor at every point for growing the tree. Whereas a random forest, every time it grows a tree, it only considers a subset of predictors to grow the tree, the root of the number of predictors. And this is getting quite statistical. And boosting grows trees sequentially. So you'll create one tree, and then based on the results of that tree, you'll grow a second tree that takes into account the previous tree. Whereas bagging and random forests just continue growing random trees and then average out the results. So boosting is sort of more sequential in the way it grows trees and creates a model. So again, you can see like machine learning, it's super simple as long as you have the data. So this is the training data. It's one line to create a machine learning model. In this case, the one line is literally just random forest. That's it. And then you can get the predictions now that you've tree 2 is what my machine learning model is called. And now I can predict using this machine learning model. This is basically now my function, my f of x that we've created. And this function does a hell of a lot of stuff. That's why you can see it's stopped over it here. But you can basically see someone else has gone and written the actual code to implement a random forest and do all of this. So out of the box, it's the same in Python. All of these machine learning models are so easy to use and so available for people. They really exist. The hard thing is all of these machine learning models have these hyperparameters. And if you don't know how a random forest works or bagging or boosting, you won't really know how to often use these hyperparameters. And that means you can often get poor results that won't extrapolate out of this use case. So yeah, while this trains, you can see we're going to do a random forest model. We even got some deep learning models over here. So here we're doing, and deep learning is the creme de la creme of hyperparameters. I study this and I studied a bit of it. I mean, I would say I only scratched the surface. And I think you have to have a PhD to know actually what these things mean and know it enough. I mean, the amount of different things you can adjust in deep learning. Deep learning is essentially a neural net. Epochs, the number of time it goes through. These are the layers of the neural net. So these are the neurons. This is a 3-layered neural net with these certain neurons. It's got dropout ratio. A lot of these things, regularization, are basically to guard against overfitting, because overfitting is so easy with these models. And yeah, I mean, it's just a dog show. You have to have a really good grasp of statistics and understanding to basically know how these different hyperparameters affect this f of x function you're creating, because you basically just don't want to overfit. You don't want to train your model too closely to your training data so that when it sees test data and other data, it's learned the noise in your training data, so it doesn't accurately predict data it hasn't seen. This tree is still going over here. I didn't think this tree would take so long. But yeah, maybe that's a good place to stop for now. There's a lot of other cool models. There's support vector machines, which you might have heard of. As you said, trees, there's random forests, bagging, boosting, deep learning, pretty much consisting of neural networks. And I think everyone's got a different way for why they call it deep learning. But when you have more than one layer in your neural network, then sometimes people call it deep learning. And the reason why deep learning has risen to such prominence sort of more recently is it requires an incredible amount of computational power to actually create these models and find these functions, especially when you have lots of layers and neurons. And in the past, there just often wasn't, 10, 20 years ago, there wasn't as much computational ability to be able to realistically train these models. And now with computers getting so much better, it's obviously a lot quicker to do. It makes neural nets much more feasible to basically do. So that's essentially what we're doing. We're using statistical methods that are taking in these predictors, all of these pixels, and from that we have digits, and we're learning through these examples, and we're trying to create a function f of x such that when we're given new pixels that we haven't seen before, our function can predict what the digit is. And now we're creating a random forest as one statistical method to essentially do that. And this category of machine learning is supervised machine learning, essentially. And this is an awesome book that goes through a lot of it. But I'm going to switch back to you guys for a second and ask a couple of questions while that random forest trains. I don't think it should take too much longer, but I don't know.
Awesome. Thanks, JonJon. Really interesting stuff. If you were to say, like, what's the first book or what's the first resource you would recommend to look into if you want to learn more about machine learning, what would you? I'm
biased. I love this book, Introduction to Statistical Learning. I find it's really good. It's also super highlighted by me. I find it's got a nice balance. It's got the mathematics behind things, but for a start, a lot of books can be overwhelming with too much mathematics. This has got a good mix between theory, statistics, giving you the mathematical processes, but also just giving you a lot of code examples, and like it's throwing you in there. You don't feel like you're going to have to do 2 years of stuff before you can get your own machine learning model out there. So I think it's quite cool. It is an R, so introduction. Python is definitely like the de facto machine learning language now, I would say. Like it's got the majority of developers and a lot of support, but R is still really cool. And I mean, if you know, R or Python, like they're both cool. They transfer. And
would you say R is more for research and Python more for production code, or?
I think R has just been historically more for statistics and statistical things, and Python can sort of do like anything, whereas R is sort of a bit more niche maybe on statistical type things. So I think there are a lot of statistical packages that I think don't exist on Python. Like there's quite a lot of hardcore stats that people do turn to R to do. But I've done most of my machine learning in R, to be honest, so I can't make a really hectic comparison. I've only done a few machine learning things in Python, but I've obviously done more normal coding in Python. I'd never turn to R to like build, I don't know, a front end for a website or something like that. I mean, it's a pretty,
I think that the same authors of this book, they also wrote elements of statistical learning.
100%. Yeah, you're totally right.
Okay, yeah, and that book is like, if you have no idea about, well, you probably need to be able to read some math symbols, but it is not nearly as difficult, I think, because the goal of this book was to actually introduce it to more people. And so if you want to start, like if you're like complete zero, then probably start from that, I guess. Would you agree, John?
Yeah, I'd totally agree. I'd say start off from introduction to machine learning is a bit more gentle, and I'd start there. And then once you've gone through that, the elements of statistical learning by the same authors, it's just, it's more comprehensive, more dense, more concrete. There's more stuff behind it. But no, I'd agree with you.
You know what? I'm actually looking at it right now, and I think maybe I've mixed it up with another book by the same author, because it does look heavy on maths.
Yeah, the elements of statistical learning is a lot more heavy than this one. This introduction is more light. Yeah.
Okay, I think I mixed up some books.
But that's like machine learning in a nutshell, or supervised learning at least. Getting your data, cleaning it, preparing it in the right form so those models can digest it, choosing which model you think would be most appropriate. Is it a tree? Is it a support vector machine? And then, understanding the hyperparameters to do it. There's an ensemble, so you could do a random forest, a support vector machine, and a neural net, and you could create a model that uses those three models as input and gives you a result. And that's quite robust. Maybe use multiple machine learning methods.
That's fascinating.
I mean, it's a crazy field. I think there's a lot of cool stuff in it, but yeah.
The idea behind this is amazing, right? How you go into Hilbert space. I mean, I don't know much about Hilbert space, but you kind of reduce the dimensionality, I think, and you do stuff in like a completely different abstract mathematical universe, and out comes the result that is actually very useful. That's absolutely amazing.
Yeah. So a big optimization I did for this that I didn't show is there were 784 pixels, so 784 predictors. And especially with deep learning, you need loads of examples, especially compared to your predictors. So I shrunk it from 784 predictors to only 60 predictors using something called principal components analysis. And that's a way you shrink your number of predictors, but retain as much predictive power as possible by creating new predictors that are basically orthogonal to each other and explain as much as dimensionality as possible. And that made my neural net perform way better, because 2,500 observations isn't actually a lot. So having 784 predictors and 2,500 observations wasn't making my neural net work very well. So yeah, that was a big improvement.
Fascinating stuff. We should do machine learning more often.
Yeah, no, it's cool stuff. Machine learning and blockchain, all the buzzwords right here on Tech Friday. So it's not going to give a result because it's still busy training, unfortunately. I think running StreamYard on my computer is chowing all my available resources, and training this tree is taking long. So I think we're just going to have to, I'll tell everyone next week, come back to find out what the tree scored for accuracy.
How's that for a hook?
Yeah.
Maybe you share the screenshot in the comments of the video.
Yeah, we can share a screenshot in the comments.
Run it. How different are the results? Like, how stochastic is it?
So the trees are pretty stochastic, pretty random. It varies. The neural nets are also pretty random, but I think ballpark it's pretty similar. I can't tell you how random it is. Yeah, I'm not sure, but it's random for sure.
Yeah,
slightly different.
Most of the neural nets have a random discount factor and stuff, so that they don't local maximum, stuff like that. So
some also use seeds if they want to reproduce the exact same models as well.
Makes sense.
Yeah.
Cool, guys.
Sweet.
So that was super interesting. I think for more details, JonJon will put all the links in the description, the books, the image of the results, everything like that. And then we'll see you next week. Anything else?
What's happening next week? Any ideas?
That'll still be a surprise. We'll have to find some.
Jason needs to figure it out.
Some eager person to talk. So that's all.
Awesome. Thanks, guys. Enjoy your weekend.
Guys.